Okay, so we've got some other questions about motion with vectors here, and we're going to go through them together. So an ice skater is skating on a large flat ice rink at time t equals 0. They're at point O, so they start off at the origin, if you like, and they have a velocity. Okay. At 20 seconds, they're traveling with this velocity. Okay, so first thing we need to notice is these values are not the same. So there must have been some acceleration. Things must have changed. So this one, which applies to some questions, is not going to be useful here because there must be some acceleration going on. Relative to O, the skater has position vector S. Okay, so they just want us to use the letter S at t seconds. Constant acceleration. Okay, so we've got constant acceleration going on. So as I said before, this isn't valuable. What do we tend to use with constant acceleration? Well, our first thought really is about suvat usually for constant acceleration. Okay, so how's this going to work with vectors? Well, for most of the suvats, you're actually fine using them as per normal. So the initial, if you like, is 2.4 and minus 0.6. Yeah, you can just write them out as vectors. Velocity is a vector, that's a vector, so it's fine. And then you could do the same for this one here. So we could do minus 5.6 and 3.4. I don't normally write it this way. I think it's a bit clumsy, but it does work just fine. In fact, in projectiles before, you might remember us doing suvat and DST and sort of doing them separately. So yeah, we can do that. We can write all the numbers separately as well if you like. The key insight is that the I and the J aspects are separate to one another. So you just kind of do your own thing for the I's and your own thing for the J's. The T is not a vector. So T here, for example, this journey is 20 seconds. So the 20 gets used with both the I and the J bits. But apart from that, they stay separate to one another. So if I want the acceleration, what suvat is useful there? It's V equals U plus AT, isn't it? So what I would do on this one is, I'm going to zoom in a little bit. So I'm going to do, what was it? V equals U plus AT. And I wanted to find the acceleration. So I'm going to do V minus U over T equals A. And I'm just going to instead do that with these vector values. So minus 5.6, 3.4 minus 2.4, minus 2.4 minus 0.6. And to make it a little bit neater, I'm going to just say I'm going to do a 20th of whatever's here. And this will give me my acceleration numbers. So I'm going to get a 20th of what then? A 20th of minus 8. And then is that just 4? Okay. And these will give me my acceleration values. So something to notice with the acceleration here is you can have a different value, again, for the I and for the J parts. So they don't have to accelerate in the same way as one another. It might be constant acceleration, but it's not constant between the I's and the J's. It doesn't have to be the same for both. So for the first bit there, yeah, minus 0.4 and 0.2. It says find an expression for S in terms of T. So what they're getting at here is now we know the acceleration value. This acceleration value is going to be the same for the whole question. So if I do S equals UT plus half AT squared, I can ignore this V bit now and I can just do 2.4T minus 0.6T. So that's the U and the T bit put together, yeah? Plus a half of the A. So let's just do this in 2 steps. So that's a minus 0.2 and a 0.1 t squared. And you can tidy that up a little bit. So you could say something like 2.4t minus 0.2 t squared and minus 0.6 t plus 0.1 t squared. So what that does is that tells you, if you give it a t value, that will tell you where the thing is. Okay, so yeah, that one's all fine. So that's my A and my B parts there done. Okay, what are we doing next? Find the time at which the skater is directly northeast. So we've spoken about this before. Northeast is going to mean that you're somewhere on this line, aren't you? So on this line, this is special because if you pick a point just to visualize, if that's 5, that bit has to be 5 as well. In other words, the I and the J values are equal to one another. Yes, that is also true. If you just think about it, that is also true down in the southwest bit as well. So we just have to check our t value that it actually works. Okay. So I'm going to just check the wording one more time, at which it is. So what I'm looking for is the language, is if it might say when it is traveling or when it is. So this is about S. So I'm just checking that the S part is correct. So the top bit is the I bit. This bit is the J bit. I'm going to set them equal to one another then. So 2.4t minus 0.2t squared equals minus 0.6t plus 0.1t squared. Everything's got t in it, so if you ignore t equals 0, you can jump to 2.4 minus 0.2t minus 0.6 plus 0.1t, and eventually you'll get to t equals 10. Okay, and for yourself, you can just check that one works if you like, but I know it works because 2.4 times 10 is 24. Okay, 10, that's 100, so it's 24 take away 20, which is 4, so the answer should be 4, 4. So t equals 10 should be when this happens. Finally, a second skater travels and they have this position vector. 11t, so where they are equals, 1.1t minus 6. So all of the stuff about acceleration, whatever, and so on, that's all been done for me. I don't need to worry about that. I just need to say that the two people are in the same place. So that just means when this position vector is the same as this position vector. And look, there's no I bit, is there? So the I bit, interesting. So I guess I'm saying 2.4t minus 0.2t squared equals 0, and minus 0.6t plus 0.1t squared equals, I think it was 1.1, what was it? It was 1.1t minus 6, and it says show that they meet together. So if I use the top equation, it's just very useful. It will lead me to t equals 0 and t equals 12. But when I use t equals 0, what you'll do is you'll find that this bit here, this is 0, this is minus 6. So 0 is not equal to minus 6. So t equals 0 is not the value that we want. So we want to use when t is equal to 12. Okay, so we're going to use t equals 12, and we're going to use it with this one here. So we would just show that we're using it. So minus 0.6 times 12 plus 0.1 times 12 squared equals, well, find out what that is. And then also do 1.1 times 12 and then minus 6. And these values should be the same as one another. And in fact, they are, yeah, 7.2. Okay, so they collide as you'll know this equals 12 because that's where you came up with it in the first place. So as I and j values the same at t equals 12. Okay, so that's kind of how you do that bit there. So this is a bit of an interesting one because they're mixing in some cases of constant acceleration, and I think we've got more of this coming up in the next part as well, which is in the exercise for 8a. But then you've got this constant speed sort of thing underneath, which has already been done for you. So I think we'll leave this one here. So we're going to do one more in the next video about constant speed, and then we'll do some more constant accelerations like this.